So, first of all, I'd like to thank the people who organized the conference for their work, and I'm grateful for being invited. This is my first time in China, and I also come from, I guess I was raised in a long, glorious, ancient culture, and I do believe that any place that has a long history and culture has a very, very steady foundation to build its future. So with that, I will proceed with my talk. I will talk about silicon carbide devices. We had some excellent talks on GaN photonics, and Umesh made an excellent presentation both for RF and GaN power devices. And what I want to do is I want to start from the electronics and show the position of power electronics, and then specifically where wide bandgap devices and more emphasis on silicon carbide where they fit in. So in the United States, the aerospace sector is the biggest export, and power electronics drivers there are in sensors, radar, propulsion, so it's a big, big area for power electronics. Automotive is number 2 in the United States. There were several slides that were shown on vehicle electrification, which is coming both with silicon carbide and GaN. Now, you will notice here that transportation does not include rail, which is a major, major area of development, but not so much for the United States, where people prefer to be in cars that are stuck on the road in heavy traffic, which I don't understand. Another area, of course, is the grid infrastructure, and there power electronics plays a major role with respect to reliability, sustainability, and flexibility. And of course, electric motor drives. This is a very big application, and variable speed drives that are very efficient are being materialized with silicon carbide devices, and of course the advantages in the weight and volume reduction. And last but not least are the data centers that Umesh also showed on his slide, and that's a playground for both silicon carbide and GaN devices. The idea is, of course, to increase the efficiency. The biggest problem with data centers is the massive heat, waste heat that's being generated. So if there's anything that can be done to manage that heat better, it's going to be revolutionary for data centers. So the electronics market as a whole is a $35 billion a year industry, and it's growing at a rate that's faster than the US GDP. And power electronics is a major part of the electronics manufacturing. As far as the aerospace is concerned, we're replacing hydraulic systems with electrical actuation, and that's a big step with respect to reliability. And also, we're moving towards the more electric aircraft, and that has very big efficiency advantages. With respect to cars, electric cars have a very, very long history. They go back to 1900 or so. And this car in particular, if you ever find yourself in Michigan and you go to the Ford Museum, this is the car that the wife of Ford was driving, right? Now, you might say, why was she not driving a car her husband is making? There were very compelling advantages for electric vehicles at the time. One of them is you didn't have to crank the car. The second thing is you didn't have to use complicated shifting mechanisms. And of course, the downfall, and this is prior to the manufacturing of the Model T that brought the price down substantially. But even before then, a big problem was range, right? In those days, in the 1900s, you bought an electric vehicle, you couldn't just go to your home and plug it in, because chances are, in rural areas, you had no electricity in your home, okay? So range is one of the problems that's being faced with electric cars today. Nevertheless, now we've come to the point where car electrification is not only in the motor, but there are major, major systems, auxiliary systems that are being electrified, and both silicon carbide and GaN have a big role to play in this very, very massive market. This is a projection that was given to me by Cree Wolfspeed, and it shows the opportunity in the automotive market. And indeed, the automotive market is massive. The companies that will be able to qualify their products and basically insert themselves in automotive, they will win. And I think the whole silicon carbide and GaN sector will win, because that will bring up the volume. And I will talk about the significance of volume in reducing prices in the next few slides. So as far as the electric grid applications are concerned, this needs an introduction. It's a major, major area of growth for wide bandgap devices. If you see Europe right there, it's got a lot of HVDC, high voltage DC networks, and it's Europe and China where HVDC is growing massively. Other areas are microgrids, solar interface, energy storage. Everything said, about 40% of the electricity passes through those systems from generation to use. Motor drives, something that we're not thinking very often about, are relatively inefficient the way they're done today. So 20 to 40% of the energy is wasted in throttles and mechanical devices, and the push now is store variable speed drives, and I will talk about why silicon carbide plays a big role there as well. So about 40% of the total US electricity demand is going into these electricity motor drives. So going to the data centers now, this is the largest data center in the world, 360,000 servers, and it's in China. And heat management when it comes to data centers is really a very key thing. And that's where GaN and silicon carbide efficiency can play a big role. And it's a very massive market. There's also major efforts in superconductivity to battle this heat management type of situation. Now, not to be outdone, the United States is building a data center that's going to be bigger than that. And I'm sure China will respond with one that's even bigger. So that's all good. Now, as with any new technology, you have all kinds of material problems you need to develop, so there have to be some very compelling advantages for you to move in that area. So what is it about silicon carbide and GaN that make them very, very good candidates for replacing silicon in power electronics? If you look at the energy gap, and some of these properties were also shown by Yumish, looking at the energy gap and the electrical breakdown field, they're much higher than silicon, which means what? If you look at the device thickness for a specific breakdown voltage, if the critical field is much bigger, like it is right here with silicon carbide and even more with GaN, then your device can be made a lot thinner, okay, for the same breakdown voltage. And what does that allow you to do? The fact that you have a thinner, smaller device allows you to operate at high frequency. And that's key because, as Yumish mentioned, it reduces significantly the size of the passive components. Just to give you an idea, this is a slide from Rome. A device that will block same breakdown voltage in silicon versus silicon carbide, you can see that it's 10 times thinner. So the fact that it's thinner means that the electrons or holes that are doing the conduction have to cross a smaller area, so your conduction losses naturally go down. The fact that it's thinner means that when you do switch these devices, you have a smaller run to switch, so you can sweep the carriers out faster. So both lower conduction and, because of the smaller size, higher frequency operations, both very, very important. Now, looking at silicon carbide in particular, the fact that just like GaN has a very big energy gap means that at room temperature you have very few thermally generated carriers, which means that at room temperature and at higher temperatures your leakage current is much lower, and that's a very important thing. And if you look at the thermal conductivity of silicon carbide, it's much, much larger than that of silicon, which means what? It means that you can basically dissipate heat very, very effectively. Now, you have to work on the module as well, because at this point the module is the bottleneck, but the fact that you have a device that can dissipate heat very fast means that you can reduce the cooling requirements. So overall, with wide bandgap devices, you're able to make them smaller in size, so lower volume, lower weight. They're more efficient, so you save energy, and more importantly, when you reduce the form factor, you're able to operate at higher frequencies, and that's key in savings. So this is some information that I'm taken from the ARPA-E agency of the Department of Energy of the United States, and it kind of gives a general idea of the silicon limit, okay? You start with IGBTs, those are bipolar devices, so you have two types of carriers doing the conduction, so that makes them very efficient as far as conduction losses are concerned. But when it comes to switching, you have now both electrons and holes to sweep out, and that means that your switching is slower, and as such, it's more lossy. Then you have the superjunction, which is a great, basically, development in silicon for a number of years. And I have to say that every time you look at silicon carbide and GaN and you talk about their compelling advantages, silicon comes around and basically strikes you really hard. I would say that there's no limit in the creativity and the work that silicon people are doing to push the material literally to their ultimate limit. But having said that, if you look at the high frequency areas and high power areas, there is a space where wide bandgap devices have an opportunity. And that translates to higher blocking voltages, higher device currents, and different applications in different areas, both for silicon carbide and GaN. And in most cases, it's not silicon carbide against GaN. In most cases, it's find the right device for the right application. And in a lot of situations, that could be silicon as well. So let's look at some advantages of silicon carbide. We talk about the automotive market and how the efficiency plays an important role. This is a project that I have with John Deere, and this is a loader that basically uses silicon carbide in its inverter. So the traction is done using silicon carbide. When I went to John Deere to basically review the project, they didn't take me into a test setting. They just basically gave me a set of keys and said, get on this and start driving, which was basically a lot of fun and a good way to kind of demonstrate the advantages of this technology. The other thing that I found striking when I got on this thing is that the control is basically a little joystick, just like the one my son is using playing video games, okay? And all along I thought he was wasting his time. In reality, he's building important skills to enter the workforce. So what this system does, it's basically the power density is much higher, about twice, and it has 25% more fuel efficiency. And this is very important because if you have something like this working in the field, you can't just drive around the corner to a gas station to fill up, okay? So the fact that it's more efficient translates in huge economic savings. Also, by electrifying the different systems here, makes control of this device much easier on the operator, which is a big advantage as well. And going to the variable speed drives, they save about they have the potential to save about 20 to 40% in energy with respect to the ones made by silicon. And the idea is that the drive basically works with the end point, the gearbox and the compressor, to basically modify the speed. Now, if you try to do this in silicon, it's very, very bulky. It has a very bulky transformer, and going from 13.8 kV to the lower voltage takes up a lot of efficiency. And there is a program in the United States to build these motor drives. And again, motor drives are about 40% of the electricity consumption in the US. So there is a program to go directly from 13.8 kV using solid-state transformers, silicon carbide electronics, to do the variable speed drive. And that's under development. It has huge, huge implications. As far as data centers are concerned, what silicon carbide and GaN allow you to do is come up with new architectures to be more efficient. And you can see this is a situation where both silicon carbide and GaN can work in harmony. You can use silicon carbide for the higher voltages, 1200 volt devices, and then you can do a lot of work in the lower voltages using GaN. Overall, data centers that are more highly efficient can manage heat a lot better, and it's a very, very big application. So what is it that we need to do to get wide bandgap volume to go up, get wide bandgap manufacturing? Of course, there has to be capital, right? We have to have investment in this technology coming from governments around the world. We need the technology innovations to drive the efforts, and Yumish and Professor Nakamura talked about those. You also need an educated workforce, right? These are new technologies, and there are new power electronics architecture. If people are not trained in how to make those happen, they will never use this device. And a big problem with silicon carbide and GaN insertion is the lack of knowledge on how to apply these devices. And you need to connect the small companies with the medium companies and the large manufacturers working together, and you need to bring in universities working with industry so students can get trained and be part of the future workforce that knows how to use these technologies. And of course, you need leadership and business-friendly environments, and that's what we do at Power America. So Power America is a U.S. Department of Energy wide bandgap manufacturing institute. It started in 2015. My budget is $140 million over a 5-year period, and the goal of Power America is to address gaps in wide bandgap technology, both silicon carbide and GaN, to enable U.S. job manufacturing creation and energy savings. So Power America has 46 members from all areas of the supply chains. We have foundry companies. We have companies that basically design devices and build modules. We're active in GaN. And of course, there are a number of companies doing wide bandgap systems like GM, Toshiba, ABB. And we have many universities that work with us. And this is where a lot of the training of the next generation workforce takes place. So I started at Power America about 2 years ago. Prior to that, I spent about 20 years in industry working primarily with silicon carbide. And when I started there, the first question is, what is it that we need to do to lower the cost, okay? And you're not going to be able to lower the cost unless you get to volume manufacturing. And the best and biggest example of that is the flat panel display. Back in 1996, I was working on flat panel displays, and a 13-inch display was $14,000 US, right? And I was thinking to myself, this is never going to take off. Well, guess what? If you have technology advancement and compelling advantages, and you get to large volume manufacturing, you will be competitive, okay? It was $14,000 at the time versus a $300, TV set, TV monitor. So you need to streamline fabrication. Whatever it is that you need to do differently with respect to silicon carbide or GaN versus silicon, you need to identify that and build high-yielding processes. Then you need to have the right modules for these devices to go in. We talked about how they have high voltage and high frequency, right? So you need special packages. Silicon packaging and modules will not do that, and you need to train the workforce. And of course, you need to improve the material quality. Material work is key. Your device is only going to be as good as the starting material, okay? And that's crucial. So investment in material quality feeds up all the way to the top of the chain to the product. So once you have those, reliability needs to be established, and that's key. You talk to people who make silicon carbide devices that will tell you that their devices are more reliable than silicon. You talk to the power electronics people who are going to basically use these devices and create the demand, and they tell you we're not so sure, right? So establishing reliability is key, and I'm investing a lot of money in this effort. And of course, you got to demonstrate compelling system advantages. In the end, if you build a system using silicon carbide or GaN, and you show the efficiency, the smaller volume and weight, all these things, that's where upper management in a company comes in and takes notice and starts using internal R&D to invest and move things forward. So having said that, we talked about how at higher frequency, the parasitics, the capacitors and the inductors get reduced in size. We need to develop those high frequency technologies as well, but that's something that we're not funding at Power America because it's not part of our mission. So once you create the device demand, then you go into large volume manufacturing, and large volume manufacturing will lower the cost and get you to the large scale wide bandgap power electronics adoption. So this is from last year, projects that I'm funding in the area of foundry, devices, building the modules, setting up third-party reliability testing to prove out the reliability of both silicon carbide and GaN devices. And of course, I'm funding commercialization applications because this is really where silicon carbide and GaN will shine and get people to notice. And finally, there's efforts going in the education and workforce development so they can use these new technologies. So overall, I start about 33 programs every year that are collaborations between industry, university, and national labs. So what are the biggest barrier to wide silicon carbide adoption from my experience? One of them is reliability. Unless a device is reliable, right, no matter how good the performance, the conversation will end there. So after people are basically convinced of the reliability, the next step is the high cost. And getting the high cost down is volume manufacturing, right? But you're going to have that when you have demand. And to create the demand, you have to have an educated workforce that within the companies will take those devices and use those devices. So, looking at silicon carbide devices, it's $1 billion a year market by 2022. And at this point, the silicon carbide MOSFET is the transistor of choice. More than 95% of the applications use silicon carbide MOSFETs for their power electronics, for their silicon carbide power electronics. And if you look at the MOSFET, there's a number of areas with the resistance, primarily the drift region, the contacts, and the channel. So this is a graph that basically gives you a lot of information on how to design your device. Okay? If you're making a device at 10,000 volts, you can see that the majority of your resistance comes from the drift layer, which is the thick layer that you need to block the 10,000 volts, right? At that point, the substrate, the channel, the other resistances are secondary. So when you design a 10 kV MOSFET, you can make the channel more robust, so the device will be more rugged, and have no penalty as far as the total resistance is concerned. If you're making a 1200 volt device, however, you see that the resistance of the drift layer and the substrate and the channel are more or less the same. So when designing these devices, you got to work in all these areas. So you got to thin the substrate, you got to design the channel to be low resistance, and there's nothing, of course, you can do with a drift layer unless you go into a super junction structure, which they do in silicon, and it's something that's very actively researched for silicon carbide. So looking at some historical data from Wolfspeed, you can see that when the MOSFET was introduced back in 2011-12 or so, going out to 2015, 2016, the cost of the device dropped about 80%. And that's a consequence of increasing the manufacturing volume, optimizing the device, but also larger wafer area plays a key role. If you look at the if you look at the 100 millimeter basically device area and you go into 150, so when you go from 4-inch to 6-inch, you get twice the material. And if you've ever worked in a foundry, you will know that the cost of the wafer to process the wafer approximately does not depend on the size of the wafer. Okay? So basically, by going into larger area wafers, you're able to reduce the price by half. And of course, we need to move fast to 8-inch wafers in order to compete more effectively with silicon. Another model that we've put together in the United States is a model where we take a legacy silicon foundry that's kind of outdated, it's doing 6-inch, and insert silicon carbide there. The investment that you need to make in order to take a silicon fab and have it process silicon carbide is relatively small. About $10 to $15 million will get you there. And the advantage of having a silicon foundry where you process silicon carbide is now you have a foundry that's basically 24/7, so it's 7 days a week, 24 hours a day, 3 shifts, right? And it's close to capacity, okay? The biggest cost in a foundry are the overhead costs. So if you're able to process silicon carbide wafers in a high volume foundry, then the cost of processing those wafers is basically split among all the wafers that are processed in that facility, and that lowers the cost. So by doing that, you can have silicon carbide production that's close to the cost of silicon, and that's a model that's been very, very successful. So where are we today? If you look at 1200 volt silicon carbide MOSFETs that are commercially available, their price is about 3 times higher than that of silicon. So the immediate reaction would be, they're too expensive, I will wait until the price drops. But what happens if you go into a system? For this specific PV inverter, despite the fact that the silicon part is 3 times less in cost than the silicon carbide semiconductor, the overall system cost for silicon carbide is lower. And why is that? It's because when you use silicon carbide, you can operate at higher frequency, and as was mentioned before, the cooling requirements get reduced because of the better thermal conductivity, this material property. And look what happens when you go from 20 kilohertz to 100 kilohertz. You have a major shrinkage in the size of the passives. You lower the volume, you lower the weight, and by doing so, you now become competitive. So when you talk prices for silicon carbide devices and GaN devices, right, don't just stay on the price of the device. Look at the whole bill of materials. It is actually more cost effective in certain applications already to use silicon carbide. The other thing that you got to take into consideration is that a silicon carbide system is more efficient. So for the whole 25 years life of the system, you're going to be saving energy the same way you put a solar panel in your home and you save energy over a number of years to basically make up for the cost. Okay, so getting close to the end, I wanted to point out the importance of training the workforce. And in the previous year, I had 19 university projects that were applied projects. So this was an opportunity for students to get involved with real-life applications. A total of $6.5 million was invested, and it was about 80 students that were trained in silicon carbide and GaN power electronics. These students will find themselves in the industry where they'll train others, or they'll find themselves becoming professors in universities where, again, they can teach wide bandgap technology to help it proliferate. There's also a need for workforce training, and that would be the existing workforce. So at Power America, we're putting together a course every year. The way we put that course together, we went to big companies like Toyota, ABB, GM, and we asked, what is it that you need to train your workforce in wide bandgap power electronics that's not available right now on the market? So they gave us the feedback, and we bring people from around the United States to teach that course. So having said that, the last comment that I would like to make is that wide bandgap technology is not a China versus Europe versus US type of competition, because we all live in the same planet, and by introducing more efficient technologies, we're going to make a better world for our children and the generations to come. So thank you very much for your attention, and I would be happy to answer any questions should you have any.